knows a lot about the science stuff. Professor Dave explains.
So far, we've discussed the electromagnetic force in the context of QED and the strong nuclear force in the context of QCD. There are two remaining fundamental forces, gravity and the weak nuclear force. Since the search for a quantum theory of gravity is still an active field of research with a lot of open scientific questions, we only have one more force in the standard model to discuss, the weak force. Also known as the weak interaction, it is mediated by the W and Z bosons. It provides a description of many important processes in physics, including nuclear beta decay and nuclear fusion, which powers the sun and other stars. But where did the theory that describes this force come from, and what is that theoretical structure? Additionally, how can we use this fundamental force to accurately describe particle behavior at the vastly different energy scales of beta decay and nuclear fusion? Let's answer these questions while examining the way that the weak force shows up in modern physics and is connected with the other components of the standard model. Let's start off by talking about the history and development of the theory behind the weak interaction. After Wolfgang Pauli proposed the presence of an unseen neutral product from beta decay to explain the apparent lack of energy conservation, the world of physics was ablaze with ideas about this new particle. Enrico Fermi called this mysterious new particle a neutrino, after its neutral charge and seemingly little mass. Fermi then developed a theory of how these neutrinos would interact, and it was creatively named Fermi's interaction. His idea was that a beta decay, which involves a neutron decaying to a proton while emitting an electron and an antineutrino, could be modeled as a four-point interaction. This means that all the particles directly interact at one vertex, with no mediators or propagators. However, it was quickly shown that this theory had one major flaw. The cross-section increases linearly with energy. This means that at high energies, the cross-section approaches infinity. This pointed towards the need to add propagators into the model of the weak interaction, and the ideas of the W and Z bosons were born. Even though Fermi's original four-point interaction was incorrect, it still provided some useful insights into the characteristics of the weak force. First, the weak force converts protons and neutrons into one another, or rather, the weak force changes quarks into other quarks. As a result, it can be responsible for processes like beta decay and nuclear fusion that converts hydrogen into helium by turning protons into neutrons. Additionally, Fermi introduced a constant in his interaction called GF, which was also creatively named the Fermi constant. This constant represents the strength of the weak interaction and is the same for all leptons. Thus, Fermi's constant is responsible for a principle known as lepton universality, which tells us that all leptons, regardless of which type, couple to the weak force bosons with the same strength. This means that any difference in decay rates or cross-section should only come down to the different lepton masses. Through extensive experimentation, this has been tested and repeatedly proven accurate. Fermi's four-point interaction can tell us some interesting aspects of the weak force, but understanding the full picture requires adding in the propagators, the W and Z bosons. These bosons are quite massive, with the W mass being 80.4 giga-electron volts per c squared, and the Z mass being 91.2 giga-electron volts per c squared, making them roughly 80 times more massive than a proton. The large mass of these bosons has three direct implications. First, at low energies, these bosons are extremely unlikely to be produced. This means that Fermi's four-point theory is effectively accurate in the low-energy regime. Second, the mass term in the cross-section formula prevents the cross-section from going to infinity at high energies. This highlights the importance of including the W and Z interaction mediators in the high-energy limit, and shines a light on another interesting part of the standard model of particle physics. While the ultimate goal is to create a theory that is accurate and detailed for all energies, the standard model often behaves differently at different energy scales. This allows physicists to use more simplified versions of theories in certain cases. In this situation, we can see that at low energies, the weak interaction can be approximated by Fermi's four-fermion theory, while at higher energies, the full theory with W and Z bosons must be used to model the correct behavior. To understand the third reason that the W and Z boson masses are important, consider the masses of the other bosons in the Standard Model, the photon and gluon. They're both massless. To understand why that matters, we can look at the Yukawa potential. This is a potential energy formula that comes from solving the klein-gordon equation and describes the force between particles. It takes the form negative g squared times e to the negative amr divided by r, where g is the coupling constant and a is a scaling constant multiplied by the mass m and the distance r. For photons and gluons, their mass being 0 means this decay factor goes away. This leads to the long-range Coulomb potential for photons. But confinement means that the gluon force is not long-range, as we discussed in the QCD tutorial. However, for bosons with large masses, like the W and Z, there is an exponential suppression of the Yukawa potential. Hence, the force is much weaker than the electromagnetic or strong force, and now we can see why it is named the weak force. Another important thing to note about the W and Z bosons is that the W boson is charged with a W plus and a W minus, while the Z is neutral. This difference gives rise to two distinct types of weak interactions, charged current and neutral current interactions, named for particle currents that appear in quantum field theory. In charged current interactions, a W boson is exchanged, which changes the electric charge of the particles involved due to the fact that the W itself has charge, and charge must be conserved. For a process like beta decay, a neutron turns into a proton by emitting a W- boson, which quickly decays into an electron and an antineutrino. These interactions can change particle flavor, such as turning a muon neutrino into a muon, or an up quark into a down quark. On the other hand, neutral current interactions involve the exchange of a Z boson and no change in electric charge occurs. For example, neutrinos can scatter electrons or quarks via Z boson exchange without changing flavor. Neutral currents were observed in 1973 at CERN, proving the existence of this interesting phenomenon. In the Standard Model, the weak force arises from a gauge symmetry group called SU2L. The SU2 is similar to the SU3 from QCD, but SU2 only contains the gauge symmetric form of 3 bosons instead of the 8 types of gluons, hence the W+, W-, and Z. The L stands for left-handed because only left-handed fermions and right-handed antifermions are doublets under SU2L. This means that these are the only states that are transformed by this gauge symmetry. This is a fundamental feature of the weak interaction, which is chiral in nature. This contrasts QCD's SU3 symmetry, which is vector-like, treating left and right-handed quarks identically. One of the most surprising and profound discoveries in 20th century physics was that the weak force violates parity symmetry. We've discussed how important symmetries and their associated conservation laws are, and how they're almost always obeyed within QED and QCD. The absolute truth of parity symmetry was a fundamental assumption that had been taken for granted throughout the development of the Standard Model. However, in the 1950s, renowned theorists Tsung-dao Li and chien-shiung began to question this assumption by studying mesons and proposed experimental tests of the validity of parity conservation. Chien-shiung Wu carried out an experiment where she studied the beta decay of cobalt-60, aligning all the nuclei spins with a magnetic field and measuring the direction that electrons were emitted. In a parity-conserved system, they would be emitted in all directions equally. However, they were emitted almost entirely in the direction of the original spin vectors. This suggests that parity isn't just violated by the weak force, but almost maximally so. Later, in 1964, Cronin and Fitch showed that the weak force also can occasionally even violate charge parity symmetry, or CP. While only approximately 0.3% of weak interactions violate CP symmetry, many physicists believe this is one of the factors that explains the current matter-antimatter asymmetry in our universe. So, in a way, we owe our existence partially to the weak interaction violating parity symmetry. Let's now dive deeper into the actual mathematics of the weak interaction. Since it is a quantum field theory, we can use a lot of the same mathematical techniques that we have previously discussed in QED and QCD. In fact, the Feynman rules for the weak interaction are almost identical to QED, but with two main changes. 1. The propagator term for the W and Z bosons is negative I times the quantity G mu nu minus Q mu Q nu divided by mass squared C squared, all over Q squared minus mass squared C squared, where Q is still the momentum of an internal line. We have to make this change because the W and Z bosons are not massless like the gluon and photon, so there are extra non-zero factors that get added in. 2. The weak interaction vertices in the Feynman diagram gain a factor of negative I times GW divided by 2 root 2 times gamma mu times the quantity 1 minus gamma to the fifth. Gamma mu is a Dirac matrix as usual, and gamma 5 is an object that combines all four Dirac matrices. GW in the weak interaction vertex factor represents the coupling constant for the weak force, similar to GE or GS for QED or QCD respectively, and can be expressed as the square root of 4 pi times the weak force equivalent of the fine structure constant. When in the low energy limit, GW can be written in terms of the Fermi constant GF. However, let's take a closer look at gamma mu times the quantity 1 minus gamma to the fifth power from the interaction vertex, also known as the quantum field current. This may seem unimportant at first, but it actually makes a powerful statement. Gamma mu is a vector, and gamma mu times gamma to the fifth is an axial vector. As we discussed, vectors change sign under parity flip, and axial vectors do not. This means that because of the fact that this term exists, there is a vector that is subtracted by an axial vector, which clearly violates parity symmetry. Fascinatingly, the revolutionary experimental discovery of parity violation also explicitly appears within the structure of the interaction itself. This is famously known as the VA, or vector-axial structure of the weak interaction. Now that we understand the way that the weak force current can be used to do calculations while simultaneously implying the parity violation of the interaction, let's talk about one interesting way that this manifests in the standard model. We mentioned previously that neutrinos interact via the weak force. Interestingly, that is the only fundamental force that they interact with. This makes them the only particle in the standard model that interacts with just one. Furthermore, due to the VA structure of the current, the weak force only interacts with left-handed fermions or right-handed antifermions, recalling that handedness refers to helicity. This is the exact same statement as earlier when we said that the SU2 group only transforms left-handed fermions. Since only left-handed neutrinos and right-handed antineutrinos will ever be produced by the weak force, and that is the only mechanism by which they can be made, those are the only handedness states of those particles in nature. Neutrinos are unique and fascinating for other reasons as well, one of which is their ability to oscillate between different types as they propagate through space, but we'll talk more about that later in the series. We've now discussed the three quantum field theories which describe forces within the standard model: QED, QCD, and the weak interaction. We've also explored some of the most important symmetries that underpin the standard model and the rest of physics, as well as the intrinsic connection between symmetries and conservation laws. At a basic level, we've learned how to conceptually and mathematically navigate through the interactions that occur between fermions and bosons. Next, we'll talk about how all these parts of the model have been put together to construct the standard model as it is today. We'll discuss the experiments that have grown and developed the model to the state it is in today, and the current experiments that are ongoing and pushing the limits of our knowledge. Then we'll explore the big questions that the standard model has yet to fully answer, and how it may be expanded on and improved in the future.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.